Hello again, I'm Bill Wagner.
And I'm James Sturdivant.
And we're here discussing object-oriented practices. We spent the first several modules discussing different ways to do polymorphism in object-oriented programming, whether that be different kinds of base classes, interfaces, abstract base classes, and so on. The rest of the modules are going to discuss other techniques that are at your disposal when you're doing object-oriented development, some of them from a different realm, like our functional programming module for the last one. Here's where we are in our course in general. We've covered the first 4 modules. We're up now to generics, which is where we introduce what's called metaprogramming or type-based metaprogramming. We're going to start talking about different ways to allow code to be created more at runtime than at compile time. Then we're going to move on to delegates and events, functional programming, and finish with some review exercises. Here we're primarily going to be focused on generics, which can be generic methods or generic classes. So different ways to instantiate part of a method or a class and let the runtime fill in some of the parameters depending on how we want to use it. It's a very, very powerful technique and is the basis of things like LINQ, different kinds of collection algorithms, different things involving the task-based threading library, and so on. So let's walk through and let's understand a little bit of how this works. We're going to go through the same 4 kinds of areas that we've done in our previous modules. We'll define what generics mean, both in a strict sense and in a practical sense of what it feels like when you're working with generics. We'll look at some of the guidelines to create generic objects. We'll look at some of the practices that will give you and guide you toward proper use of generics. And then we'll look at some things where if you're reviewing code, you can look at to see, is this a good use of generics and a good place to solve a problem with generic types. So let's start with that definition of generics.
Generics allow you to define a class or a method that specify a type of arguments or return values at the time of instantiation. Now, that sounds like another one of those definitions where it's hard to understand. But in fact, as a developer, you're actually using these probably in your everyday programming. So when you instantiate a list of integers or a list of strings, you're actually using generics there. And when you do that, you get some type safety out of the generics, which allow you to not add the wrong type of objects to your list. So if you instantiate a type of string, if you instantiate a list of strings, you're not going to be able to add integers to those strings. And that's some of the really strong advantages that we get out of generics.
Right. One of the ways that I've described that to different developers that are new to the concept is, you can think of the idea of if you were to write that whole class specifically to write a list of strings. And then if you were just to do a text substitution and every place you saw string, replace that with int. That's what generics do, but the compiler does all that work for you. So you write the generic class once, and the compiler replaces that type parameter, that we see list of t usually, and it replaces that t with specifically string or int every place that you've used it in the definition. So it's a way to let the compiler do that copy-paste kind of reuse that we might have previously tried to do, but let it do it in such a way that we only have to maintain one copy of that code. So that's the kind of reuse that we're getting with generics.
So some of the language support that we get for generics is through generic methods. We get it also through interfaces, classes, and then finally we'll talk about constraints. So generic methods allow us to specify the arguments that go into the method as a generic type. And we can also specify the return value. This allows us to be able to specify the type that we're using at the time that we're calling the method. And that allows us to really make that a really generic algorithm and use it how we want to at the time.
Right. So if we looked at some of the things that we looked at yesterday, we looked at that interface for iComparable, which has that compare to method. And in the classic non-generic version, the parameter to compare to is an object. And inside the implementation, where we're looking at the base class libraries, what the code has to do is take that object and downcast it to the specific type to see if it matches the type that we're working on. So the compare to for string has to take an object and cast it to see if it's really a string. We'll see later as we look through the generic code review that we can see generic interfaces for iComparable of t, which has a compare to, where that parameter is now a type parameter. It's named T in the source code.
And what that does is it allows us to be able to access those properties on that type at the time we're accessing them. So we can check to see if the string has a length. We can check for the functions. We can use any of the functions that are on that type that we specify.
Right. Once we've specifically made that it's compared to with a string, then it'll match that method. Right. And then the classes would be things like list of T, where maybe one of the properties or fields inside that class is one of the type parameters. So you end up like James mentioned list of T when he was doing that first example. It's like an array list, but instead of storing system.object references, which could be anything, it will store specifically integers or strings or teachers or students or whatever in our different exercises. And then finally, constraints to define those. In .NET, when we write a generic method or a generic class, that type parameter could be anything, right? That's sort of what we're trying to do with generics. And when we write it that way, the only things that the compiler knows about that would be there on that particular parameter would be the methods in system.object, because that's the ultimate base class of everything in .NET. So by specifying constraints, we can say whatever this type is, it must satisfy some other contract. You know, whether that be implementing an interface, having a particular base class, being a class or a struct, or having a constructor. Those are the kinds of constraints that we can specify on a particular generic type parameter. So what kind of things do we do in general with generics? As James mentioned, you've probably already used them. We're going to talk about why they were used in certain areas and why these are the kinds of different problems generics really are a great solution for. So in practice, what we'll see when we create methods is that there are type parameters for at least one argument or for the return value, and sometimes for both. You know, if you've done any link queries, you've created instantiations of several generic methods. You know, there's func of T, which is a function type that returns a type T, you know, which is used in, say, select method is one that's got two parameters, one that comes in, one for T, a different type of T that comes out. There's a select, which would be a func of T comma bool. So it has to return a Boolean, but the input type could be any type that's coming in on your selector. System.link.enumerable has got a lot of those generic methods that are used to fill out all the rich functionality in link. So that's one of the big areas where we see a lot of generic functions and generic methods. iComparable is another. There's some from task based methods for creating a task that's finished or running a task. Those are different generic methods.
Yeah, and you see that specifically on the count on enumerable, the link enumerable interface. You actually see that with the count method. You don't need to necessarily know the type to be able to count the number of items in the list, and so that's a really great example of this function where you can use that as a method to count the number of items in the list.
So then, in addition to generic methods, there's a lot of examples in the framework of using generic interfaces. So that's a type where we have a type parameter for at least one of the arguments or the return value, once again, for a common contract of unrelated types. You know, we've talked about one of those already, that iComparable of T, which would contrast with iComparable. There's also iEquatable of T, which compares two different objects of the same type for equality. Enumerable of T, which provides the basis for link once again. Those are some other examples that we can look at and see exactly how some of those work. Again, it's an interface, and at least some of the methods return or take type parameters as their arguments that will be filled in when you instantiate it in a particular way. And then finally, we have those generic classes. So in those, one of the big distinctions is that type parameter is going to be used for some field or some property in a class. And one guidance that I give a lot of developers is that if you're creating a generic class and you never use the type parameter as one of the fields or one of the members, consider making those generic members of that class instead of making the entire class generic, because there isn't any actual storage in an object that is required to use one of the type parameters, and the methods can be instantiated multiple times on just a single instance of the non-generic class. And again, we have examples there for things like list of T, which we've talked about, task of T. There are different dictionary classes as well, dictionary of string, comma, int, or whatever that we can use. And once again, we'll get different types there, and we'll be able to use those type parameters as part of the storage used by that object.
Yeah, so one example that I like to use from when I've worked with clients in the past is I had to build a box builder that would take a bunch of different items and put them into the box. And now I didn't necessarily know much information about the items, so if they said I needed to put an apple into that box, I could check the volume of the apple and then compare how much space was left in that box. And if there was enough space, I could put the apple in. Now, the requirements changed over time, and so I had to put an orange into the box. And so I looked at that generic algorithm that I did with apples, and it was the same kind of thing, where an orange has a volume, and I knew how much was left in the box. And so I was able to pass that type into that algorithm that calculated the location and how much space would go, how much items could fit into that box. And so I was able to make that a really generic instance there.
Okay, so the idea of that likely leads right into our next topic, where we talk about constraints. So constraints define some of the requirements on a type parameter. So the kinds of things you can specify as a constraint is you can specify that any type used as the type parameter must support a certain interface or any number of interfaces. You can specify a single base class. You can specify that it must have a parameterless constructor. And you can specify that it must be a class or it must be a struct. You can't specify both of those. They're mutually exclusive. So in your example there, it sounds like you would probably have to define some kind of an interface to be able to say that anything I'm going to put in the box must have a method to calculate the volume.
That's correct. So I created an interface called iPackable, and I put that on apples, I put it on oranges, I put it on brownies, I put it on all the things that were packable. We also had this idea of being able to deliver these boxes around. And so in our code base, we actually had a object called a vehicle, and that vehicle wasn't packable. And because it didn't have that interface on it, I wasn't able to actually be able to add that into, I couldn't pack that with my algorithm because it didn't fit that interface.
Right, and that definitely makes sense. That's by having those constraints, you can be as generic as you want to be, but you don't have to accept absolutely everything as something that you want to work with. Sounds good. And then, so let's look at some of the guidelines in terms of how do we look at problems and say this is something where generics is the right solution, right? How do we find some of those, and how do we know we're using these correctly when we work with our different designs? So the first guideline I try to give developers is to just be as generic as possible. And that can be hard when you're first coming up with an algorithm. So maybe we can go back to your box example where, if you start with something specific and you see how some things work, and you see that this is useful, and then you can find, okay, now I think this is useful in other places. So how, just like we were talking in the earlier modules about factoring things into base classes, here we're looking at, can I factor this functionality out into a generic type with a type parameter and then reuse it broadly across a spectrum of all kinds of different things?
Yeah, and so we actually saw you do that with the teacher example in one of the solutions that we came up with. You started at the higher level of the teacher, and you saw, hey, this looks very similar to what I'm going to be using for our teaching assistant. Mm-hmm. And so you started there, and then you extracted those specific components back out into an interface. Mm-hmm. And so we can do the same thing here with generics. Right,
and I think this is how a lot of these techniques work together in different ways, right? If I want to build a generic that's not so broad-based that it accepts absolutely everything, like some of our examples from the framework, and I want to specify constraints, what I need to do is define some interface contract that's small and well-contained, which can then become the constraint for some set of algorithms on top of this very generic type now that supports a certain interface contract. So I can get some functionality there, and I can say this is what has to be there for this to work. Mm-hmm. Okay, and over time as we do that more, that's that last idea in this: be as generic as possible. We learn to separate specific from general algorithms, and we'll really stress this as we go through the code review. When we look at the collections like list of T, for instance, there's a generic part of that algorithm, which is I want to take a linear storage block and store some sequence of items in that linear storage block. I want to let it grow when I add new items. I want to be able to shrink the storage when I remove items. Okay, that's very generic. I can put anything in there. And the specific part has to do with what kind of thing can I put in this list, and how do I make sure that I can only put certain kinds of things in this list. Sorting is another one. It has that generic part, which is if I can compare two things and know which one is greater than the other, I can put them in order. But there's this specific part that says, in order to compare two things and put them in order, I need to know which one of these two is greater than the other based on how I want to order them. And when we start to separate those, then we get a lot of the power out of these generic structures, generic classes that we can build.
Yeah, I think that's one of the things that keeps on coming up in every single one of these modules, is that we're trying to learn to separate general from specific. And then we're seeing all these different techniques that we're able to use, whether it's generics or interfaces or abstract classes, to be able to accomplish that in our code. And one of the things we're trying to do here is determine which is the best implementation, which is the best practice we should use to approach that.
Right. And I have to admit, there's times when I worry about that best practice word. It makes it sound like there should be no argument about this. Right?
Yeah.
This is the best way to do it. And for any problem that I've seen, there's usually a range of different ways that you could solve it. And, as we stressed when we've been talking about some of the review exercises, there may be, your solution may not look exactly like ours. And that doesn't necessarily mean it's wrong. It just means you looked at a slightly different way. And this gets to one of the last things that I want to kind of lead into on this guideline, is this idea that one of the ways that we can handle that specific part of the application is by using delegates, which is going to be the focus of our next module, where if I can define a specific delegate for a specific need, and then I can create this generic algorithm that's almost all the way done, but needs some little bit of code or some little bit of work from a specific type in a specific instance. And again, sorting, I think, is the classic example of that. I can sort things as long as whatever type that I'm sorting can specify which one comes first and which one comes later. And delegates can define that specific capability that I need for a certain algorithm. So with that, let's move on to that practices section. What are we trying to do when we're actually writing code and when we try to put this together and deliver things? I sort of hate to start with this in a way because of what we spent the last few hours doing, but I think it's because of habit and because object-oriented has such a history of saying, everything's about polymorphism, is to really think about preferring generics to polymorphism. If you look at the classic example of the containers, they work because what they stored was references to system.object. So I could make an array list, and I could put absolutely anything in that array list. Okay, I could make one array list that contained teachers, students, TAs, and maybe a class definition and maybe a grade for a particular assignment. That may sound like bugs, actually, because I'm putting all these different things in this one list, and that's probably not what I intended.
Yeah, and when you do that in particular, you're going to be starting to add all these if statements and else statements to make sure that you're handling the right particular object.
Right.
And so this is where being able to use generics is going to be able to help you avoid some of that if and else statements.
And the design is really that I wanted to make a list of the entire faculty. So it's really a list of teachers. And I just made a mistake by adding a student into it. So by being generic and by specifying a type parameter, once we get to compile that code that says this is a list of teachers, well, then we're able to go with just that object. And we avoid that downcasting idea, which is I've got system.object and I need to downcast it to the specific derived cast it is, which is exactly what you're saying. I need to look and see if it's a particular type, have an if statement and go, well, it is that type, then I can do extra work. That's a lot of extra code that hopefully the language can mean we don't need to write. And then the other big practice that we look at, we talked a bit about your one example there, is that we start with those specific algorithms. We start with something that we know works and solve one problem. And then we look at that solution and we say, does the code that we've written apply in other instances? And if so, how? Right? How can we take this one algorithm of putting apples in boxes and making sure the certain number fits, and then say, well, what do we do with that now if it's other things that we want to store, whether it's oranges or pineapples or ears of corn or everything else? How do we structure that algorithm and separate generic things from the specific stuff. And when the opportunity presents itself to build those generic types, then we get code that's much, much more reusable. And that's one of the things we want to do. But I think it's really hard to see a problem and see only one specific instance of it and then know, gee, this should be generic.
Right, yeah, I think over time, as you practice these various implementations of generics and interfaces and all those kinds of things, you're going to be able to see that a little bit easier. But when you're first starting out, it's going to be very hard to be able to identify where you should potentially use the generics. And so by building it out the way that you know how to initially, later on you can then come back to it, revisit it, and take a look and say, hey, this looks exactly like an algorithm that I've already implemented. And any time where you feel like you want to do that copy paste to move that algorithm in, that's maybe a good opportunity to take a look at generics.
And that's actually, I think, one of the big keys. As soon as I find myself copying a large section of code, hitting copy paste and starting to modify, I really want to stop myself and really look at it and say, is there a different tool here to do this without doing that copy paste part? And with that, then one of the last things to do, because it isn't just it's really a continuum of how generic is something, is we'll start to think about what are the constraints on a generic algorithm. So I want to leverage those constraints so that my algorithm still works. I still have the capabilities I need of any object I'm working with. And instead of maybe downcasting it to something, I should specify that as a constraint, right? Like in your example where we were working with the volume of a box or volume of what goes in a box, I could have downcast it to something and say, okay, if the thing I'm trying to put in is an iPackable, then I can do something with it, otherwise throw an exception. But by specifying the constraint on the generic algorithm, you say the only thing you can call this with is something that supports that interface. And then we can try to keep those constraints in place to say this only works with certain types that have certain capabilities. We do want to keep those as minimal as possible because that does provide as much reuse as we can get. But we do want to use them to make sure we're not adding extra code to do type checking inside a generic algorithm.
Yeah, when you start to talk about adding too many constraints onto your generics, what happens is you start to go back to only being able to use one type with your class. And so if you do find you can only use this specific base class or this single leaf class that you have, then you're going to maybe go back and rethink whether or not you should actually be using generics here. Are you adding too much complexity to the code by adding generics in?
Mm-hmm. Okay, and with that, let's look at some of the last section of what are the good outcomes with generics? What kind of things do we see in our code when we're doing them correctly? And as a counterexample of that, what kind of things would we see in our code that says maybe this is a place where we should leverage generics better? So one of the first things that we get, it's again sort of a computer sciencey word, but we get that reuse via metaprogramming. So I get type-safe reuse. I'm letting the compiler copy and paste and replace that T or T1, T2 with a specific type. And I get to avoid that idea of saying, this works with system.object and I'll downcast it when I use it. We still use system.object, but only when that's really what we wanted. And we avoid that copy, paste, and modify the parameters kind of reuse. And that's what we see is when we say, all right, if I see that, then this should be a generic. And those are really some of the first ones that I really look for seeing that reuse when I'm reviewing someone's code base and they ask me how it could be better. And
Yep, and then I would say the next really nice outcome that we get from using generics is that we minimize the downcasting that we have to do. So we no longer have to cast that object into the interface that we want to use or the object that we want to use. And we kind of touched upon this already, but anytime you have to start checking for the types, you're potentially violating the Liskov principle, and that's going to cause some sort of bug long term for you because you might not end up with the right type at the time that you get it. And so these generics really give you the ability to use that type safety that we talked about and use it to the best advantage so that you don't have to worry about casting and doing all that kind of stuff.
Right, because those downcasts can fail at runtime, and then we're going to throw exceptions, and then we have to somehow recover at runtime. If I can make it fail at compile time, You know, I can't deliver that code. I don't have to have QA test it. There's no way a bug gets found in the field because I can't deliver the code that doesn't compile. So that's why we're trying to stress that, to push that toward letting our tools find those statically as we're doing the development. And with that, I think we've covered generics pretty well, so a lot of the concepts. We'll come back in a few moments. We'll look at some of the examples that are inside the .NET framework and how they've extended algorithms to make them more generic, and provide some examples as to how you can use them in your own code. See you soon.